Hello friends, I am Jaydeep. So today we are going to see the numerical part of the sliding contact bearings. We know up till now we have seen theoretical part of the sliding contact bearing. So first of all I will request you to go through a part which already uploaded in the WhatsApp group, the video by Professor L.S.Dhamande sir. So in that they have already told the theory behind the hydrodynamic general bearing, or we can say sliding contact bearing. It is the 6th unit of your DMA2, and that carries weightage for numerical as well as theory. If we are going through previous question paper, we will come to know that theory and numericals are asked for 12 marks directly. So we will come to know how much important this topic is, numerical part of the sliding contact bearing. Fine. So today we will go through the formulas that is being used for the sliding contact bearing, and then we will see some numericals. Numericals may be asked from the numericals that we are going to see. First of all, solve numericals, and then we are going to see the numericals from the question paper. 12 mark numericals will be asked, and those numericals will have certain formula and certain chart. How to use those chart and formula, that we'll see now. After this we'll start with the numerical. Fine. So what is the syllabus? If you go through the syllabus, we'll come to know that it's unit number 6. First part is classification of sliding contact bearing, and second is the lubricating oil. So these two topics are purely theoretical, or we can say conceptual one, and you can make notes of it, and you can easily prepare for it. Next part is hydrodynamic lubrication. It basically contains derivations and numerical part. So we are going to focus on the numerical part. Theoretical part already being discussed by the Dr. Dhamande sir. So in that case, if you go through the syllabus, theory of hydrodynamic lubrication, pressure development in oil film, 2D basic Reynolds equation, Summerfield number, Raimondi and Boynt method, thermal consideration, parameters of bearing design, length to diameter ratio, unit bearing pressure, radial clearance, and minimum oil fill thickness. So whatever things, we start from Summerfield number to the minimum oil film thickness. This contains formulas, and depending on this we have to solve the numericals. Okay. Thermal considerations also, so small formulas are there. We have to use those formulas. We have to find out how much temperature rise takes place in the lubricating oil. Fine. So next part we will go through now. So what to study in this? In this we have to first of all study what is the hydrodynamic general bearing. Again I am going through a part which is required to understand, the numerical hydrodynamic general. What is the basic concept? Second is all dimensionless numbers of hydrodynamic general bearing, that comes under Raimondi and Boynt's method. Next is terms of hydrodynamic general bearing, what are different terms used over there, and then dimensionless performance parameter chart, how to use that parameter chart for the purpose of solving numericals. And next one is temperature rise in the bearing, and last one we are going through the summary. I'm not going through the derivation of each and everything, but whatever important things are there, I'm going to focus on that. Fine. So here first of all, here we are having the side view and front view of front side view of the general bearing. You can see now what the bearing is and what the journal is. So there is a difference in the bearing and journal. Journal is generally a rotating part of the hydrodynamic journal bearing. Okay. Then shaft is a rotating member, or that is also called as journal. There is a basic difference between shaft and journal. What is shaft? Shaft is having, you can see the shaft is having some high length, but part of the shaft which is present in the bearing is called as journal. Bearing is generally a stationary part. Inside the bearing, journal is present. So there are two parts, journal and bearing. Now what are different terms in this hydrodynamic journal bearing? So this is fully developed hydrodynamic journal bearing, so that there is a clearance between shaft, there is a clearance between shaft or journal and bearing. You can see there is a clearance. Your shaft and bearings are not in contact with each other. Initially those are in contact with each other, but as the speed of the shaft so bearing is a stationary outside. Okay, initially there is a contact. As full speed of the shafts, that means when shaft rotating with the full speed, at that time contact between bearing and journal lost, and we can say perfectly hydrodynamic journal bearing is working and wedging action is taking place. So in this case, hydrodynamic journal action, that means it is fully developed hydrodynamic journal bearing, and we will also have this case only. Okay, so what are different parameters of this? First of all, we will see small e. Small e is nothing but eccentricity between the bearing and shaft. You can see O is the center of the bearing, O dash is the center of shaft. So linear distance between O dash and O is nothing but your eccentricity. Small r is the radius of the journal, capital R is the radius of the bearing, ns is the speed of journal in rps, that is revolutions per second, not in rpm, revolutions per minute. It is not in rpm, that's why it is ns. That's why it is ns. I will show you this. It is ns. ns is nothing but revolutions per minute. ns is nothing but revolution per second. Okay, this one is revolution per second. Fine. So you can see now shaft and journal. So and L is the length of the bearing itself. Now we'll go through the part from this. Okay, so it is visible now. So C is the clearance. Okay, what is the clearance? Radial clearance. When O and O dash, when O and O dash are at a center, that means O dash and O, when eccentricity is 0, at that time your R, capital R minus small r, this distance will give you the radial clearance, where R is radius of bearing, small r is the radius of journal. Now next is epsilon. Epsilon is nothing but E by C. What is E? Eccentricity, and C is radial clearance. The ratio of these two is nothing but called an eccentricity ratio. So this is our first dimensionless parameter, eccentricity ratio. So from figure we can write capital R is equal to E plus R plus H0. Small e is nothing but eccentricity plus R plus H0. So you can easily see from, so O up to this distance, O to here. So O to this eccentricity plus R plus H0, these are nothing but your total radius, capital R. So R is equal to E plus R plus H0. So what is H0? If you observe this, H0 is nothing but minimum oil film thickness. So we can see that this is total, green one is oil film thickness. So oil film thickness is maximum in this region, and when we are going towards a region where oil film thickness go on decreasing, at a particular point you are getting minimum oil film thickness. You are getting a minimum oil film thickness, that is called as H0. H0 is minimum oil film thickness. So capital R is equal to E plus R plus H0. E plus R plus H0. Fine. So we are having the equation C is equal to R minus R. We'll put the value of R in this equation, E plus R plus H0 minus R. So R will get cancelled, and C, clearance, is equal to E plus H0. What is my E from this equation? Eccentricity E is equal to, if you do cross multiplication, it will be epsilon into C. So I'll put my value epsilon into C plus H0, and finally I am getting C minus epsilon C minus H0. I want to get this epsilon here, so epsilon will be equal to 1 minus H0 by C. Epsilon is equal to 1 minus H0 by C. We are going to see our second dimensionless number, that is H0 by C. So H0 by C is called as minimum film thickness variable. H0 by C is called as minimum film thickness variable. So up till now we have seen two dimensionless number. First one is eccentricity, second one is the H0 by C, called as a minimum film thickness variable. You note down these two important things. Fine. So next part is, next dimensionless number we are going to see is the important one, is the Sommerfeld number. So Sommerfeld number is equal to R by C bracket square mu ns by p. You don't bother about this derivation, how this equation is obtained. You simply keep it in mind what the Sommerfeld number is. Sommerfeld number is a dimensionless number having value R by C bracket square mu ns by p. So what are different terms present in this? So mu is nothing but viscosity of lubricant in Newton second per meter square. So this is very important thing, mu, because mu has a different unit given in the numerical, and which unit is the SI unit? Newton second per meter square. Now here Newton per meter square is Pascal, so Pascal second is another unit of the mu. So there are two viscosity, one is kinematic viscosity and second one is the dynamic viscosity. Mu is nothing but a dynamic viscosity, viscosity of lubricant in Newton second per meter square. Ns is nothing but a journal speed in revolution per second, not in RPM. P is the unit bearing pressure, that is load per unit projected area. So what is the load acting per unit projected area is nothing but your small p. Capital SC is the number which contains all design parameters of the bearing. You can see now R, C, then Ns, P, these are the design parameters. So S contains all your design parameter. Now phi is the angle of eccentricity or attitude angle. So where this angle is, I forgot to mention this angle. So in this case, this angle between where you are getting minimum H0, that is minimum oil film thickness, and vertical line. Okay, so let me mark this angle. I forgot to mention that angle here. Let us try to see which angle. So this angle is my phi. This is my angle phi. Okay, this is my angle phi. So phi is nothing but attitude angle. Yes, you might have obtained now, or angle of eccentricity or attitude angle. Now CFV is nothing but coefficient friction. The next number, dimensionless number we are going to see is the coefficient of friction variable. So what is the coefficient of friction variable? CFV is R by C into F. R is nothing but radius, C is the clearance. So R by C into F is equal to coefficient of friction variable. Now what is F? F is nothing but coefficient of friction. Up till now we have seen mu as a coefficient of friction, but mu is used for the viscosity, so we are using small f as a coefficient of friction. Now what is the frictional torque then? We are talking about the friction. Then what will be friction torque? Friction torque will be equal to force into radius. Now what is the force? Force will be a friction force, that is nothing but F into W. W is the load acting on the shaft. Okay, I can go through the previous slide, you will come to know. Yeah, so here W is nothing but the load. So how this load is acting? You know that shaft contains different parts on it, like gears, maybe there some rotating members are there, so those contains their load. So that load is converted into a point load W. So W is nothing but the load acting on the shaft. So if we see this, F into W, that is frictional force into radius, will give the frictional torque. Next one is the frictional power. Okay, this is quite important, frictional power, because some power is given, suppose 2 kilowatt power is given. Out of 2 kilowatt power, how much power is wasted in friction, that we have to find out. Okay, so basic equation of the power is nothing but 2 pi nt upon 60. Now we know that n by 60, we know that n by 60 is nothing but ms, so we put n by 60 as ns. And torque, we know what is your torque now. Torque is Fw into R Newton mm. So Fwr if we put here and n by 60 as ns, so what equation I am getting then? I am getting this equation, 2 pi ns into F into W into R, right? These are my equations I am getting here. So up till now we have seen some parameters. Let me erase these things. Yeah, so we have seen up to now some dimensionless parameter. First one is nothing but your eccentricity ratio E by C. Second is epsilon is equal to 1 minus h0 by c, so second is h0 by c. Next is Summerfield number, that is r by c bracket square mu n s by p. Then coefficient friction variable r by c. Next one is the flow variable fp. So what is our flow variable now? Flow variable is equal to q upon rc into nsl. Now what are different terms here? Q is nothing but flow of lubricant. So what is, at what rate your lubricant is flowing, that is an mm cube per second. We know like discharge, in fluid mechanics also we have seen the discharge is measured in mm cube per second or meter cube per second. So q is mm cube per second in small quantities, not in large quantity, that's why we are considering mm cube per second. L is length of the bearing. What is the length of bearing in mm? So we are getting one more flow variable as q upon rc into nsl. Next dimensionless number is qs by q, and next is p by px. So qs by q, qs is nothing but side leakage. We know that when we are pouring oil, that does not rotate only, it will also move in the axial direction. So how much is the side leakage? Qs divided by q. Q is known to us, q upon rc nsl. From this we can find out q, and we can find out the qs by q also. This is one more dimensionless number. Next is p upon p max. We know that as we are moving towards wedge, or we can say as we are moving toward this center, this part of the hydrodynamic lubrication, the pressure will go on increasing. So at a certain point there will be a maximum pressure. So ratio of p upon p max is nothing but one more dimensionless number, p upon p max. So p is nothing but a pressure at which oil is supplied to the bearing, and p max is the maximum pressure generated. Now generally for hydrodynamic general bearing, the pressure, inlet pressure, or the small p is nothing but atmospheric pressure. At atmospheric pressure we are pouring the oil. Okay, so p upon p max is nothing but the ratio, and it is also one more dimensionless number. So we can figure out how many dimensionless number we have seen up till now. So again I will revise in short. First one we have seen as yes, epsilon, that is eccentricity ratio. Second we have seen h0 by c. Next we have seen Summerfield number. Next we have seen coefficient of variable. Next we have seen flow variable. Next is qs by q, and next means p upon p max. So note down all these dimensionless parameters. Those are very crucial while solving the numericals. Okay, along with this we have also seen some formulas related to calculation of torque, frictional torque, and how much power is lost in the friction. So these two additional things we have seen. So dimensionless numbers are over. Okay, now how these dimensionless numbers are used? For that, dimensionless performance parameter for full journal bearing with the side flow I will show. Okay, now see. So here L by D is the ratio of length to the diameter. Okay, L by D. If it is infinite, it is 1, it is 1 by 2, it is 1 by 4. Accordingly we have to select. Fine. So here if L by 2 is infinity, so first of all what we are going to calculate? L by D. So L by D, if it is infinity, then what will be the values of this? So first of all, if we calculate this infinity, we will come to know that yes, only first part we have to use to solve our numerical. Only we have to use the first part, this much portion. L by D is 1. If the L by D is 1, then we are going to use the second part. Then L by D is equal to 1 by 2, third part. L by D is equal to 1 by 4, fourth part we are going to use. Okay. Now we can see here index here. In this epsilon is first dimensionless number, that is called as eccentricity ratio. Second one is the H0 by C. H0 by C is nothing but your which ratio? Minimum oil film thickness variable. Then S is Sommerfeld number. Phi is the angle, eccentricity angle. Then R by Cn to F, it is a coefficient friction variable. Q upon RCNSL, it is a flow variable. Then we have seen Qs by Q. Then we have seen P upon P max. So first of all we are going to find out L by D. Then we are going to find out some of the parameters and which row is useful to us, that we are going to see. So whether 0.1 or row of 0.2, 0.4 like. So while solving numericals we will come to this chart is given in the numerical. Need not to bother about this from where we are getting this chart. This chart or part from this chart will be given to you in the examination to solve the numerical. Okay. Next again important point is temperature rise. So temperature rise. So when oil is flowing through the bearing, obviously due to friction the temperature of the oil will increase. So how much is the rise in temperature, that we have to find out. So that is nothing but given by symbol delta T. So final temperature minus initial temperature increases, so that will be delta T, which is given by the equation 4 pi P upon rho Cp Cfp upon Fp. Now we will see what are different rho, Cp and other parts. Okay, so rho is nothing but the density of oil, whatever density of oil is used. Generally it is 0.86. Density or specific density, they can give a dimensionless number or density. If you divide by 1000, that will give you dimensionless number also. Okay, and Cp is nothing but specific it at constant pressure. So Cp is 1.76 kilojoule per kg degree centigrade. These two values are mostly used for all lubricants, but sometimes if these values are provided, then if we put this value in this equation, we will come to know that delta T is equal to 8.3 P upon Cfp upon Fp. That means if we put rho and if we put Cp, 4 pi upon Cp will give the factor 8.3 P upon Cfp upon Fp. So what is the average temperature? Average temperature is equal to Ti plus delta T by 2. So Ti is nothing but your inlet temperature and delta T is the rise in temperature. So that will be the average temperature of the oil. Now what is the average? Okay, then one more thing, if these two values are not provided, okay, if these two values are not provided, they can then we can use this formula directly, 8.3 P Cfp upon Fp. But some values like rho and Cp, another values are provided, we have to use this formula. You don't bother about the derivation of this formula. We are, as far as numericals are concerned, right now we are not going through the derivation of this, but derivation is based on the thermodynamic equation Q is equal to mCp delta T, where Q is the heat generated. So depending on that theory of thermodynamics, heat generation, this temperature rise is derived. Okay, if you are interested, you can go through the videos of theory, you will come to know that. Okay, now what is the summary? Summary is nothing but first of all basically we have to understand the hydrodynamic journal bearing. Okay, so we understood this, what is the hydrodynamic journal bearing is. Second one is we have listed out important terms. So we have seen the diagram. From the diagram we have seen different terms like H0, R, capital R, C, etc. then we have understood. So with the knowledge of some important terms, we have understood what are different dimensionless parameter. Like first dimensional parameter eccentricity ratio is 0 by c, second one is the Sommerfeld number, fourth one is coefficient of friction variable, next one is friction variable, then q upon qs and p upon p max. These are your dimensionless parameter. Then we have seen the equation of temperature range. Fine. So this is the part which is being taken by me. Now what is the responsibility? Your responsibility is very simple. You have to make the list of all the formulas. Whatever formulas we have gone through, you have to make the simple list of it, and what the meaning of those terms you have to make its list also. And once it is made, you are ready for the numerical part. And you can go through this slide 2-3 times. Once you remember it, it becomes very easy to solve the numerical. So again I am repeating, these numericals are asked for the 12 mark. If you are knowing this dimensionless parameter, any numerical based on the hydrodynamic journal bearing you can easily solve. You can easily get 12 out of 12 mark. That what I meant to say is, if you don't bother about the theory also, I am not saying that you don't prepare a theory, you prepare theory also, but if you concentrate more on the numericals, you are going to get benefit from that. So though this looks little bit difficult, you go through the slides only 2-3 times, you will easily come to know how to get the marks out of this. So it's very easy to get the marks from the hydrodynamic journal bearing. Fine. So fine, today stop here. In next lecture we will see how to solve the numericals. We will take a numerical from the, again I am telling this, you refer book by Professor V.B. Bhandari, Design of Machine Elements. That book is very good for the purpose of hydrodynamic journal bearing. So we are going to see the short example from that book, then we are going through the numericals from the question paper. Okay, so today we'll stop here. Remaining part we'll see in the next lecture. Thank you.